The problem asks us to determine which of these are polar. First, I'm going to start by drawing the Lewis structure. Then we're going to find the bond dipoles based on their electronegativity. And then we're going to find the net molecular dipoles based on the molecular geometries. Through these steps, we will determine whether the molecule is polar or nonpolar. I'm first going to start by drawing the Lewis structure of SO3. You start by placing your S atom with your O atoms around it. This has 24 valence electrons in it. We use these valence electrons to fill the outside atoms first, these three, until they reach an octet. We have already used 2, 4, 6 electrons to make these bonds, so we're going to subtract 6 from this, and that equals 18. Now we'll place the rest of these 18 electrons on the outside atoms to create octets and see what we have left over. So this will be 6, this will be 12, and this will be 18. Since we've used all the electrons and all the O atoms have octets, we can see that the S atom does not have an octet. We have to make a double bond, so we can move this pair of electrons up to form a double bond. So now I'm going to draw the Lewis structure with the double bond. So you have your S, your O, and your other O, and you have these electrons, but on this one you'll add a double bond and you'll only have 4, but these all create octets. The highest electronegative atom will have a partial negative charge, and in this case that is O. So we'll have partial negatives on all the O's. That means that there will be a partial positive on S. The positive tail will be next to the most positive atom, the partial positive, on all the sides, and the negative, the arrow will be pointing toward. Negative here and positive here. So now we need to find the molecular geometry of this molecule. This has 3 domains, so it's trigonal planar, and since it has no non-bonding pairs, its molecular geometry is also trigonal planar. When we draw that, we have S here, we have an O, and then we have an O here, and an O here. Again, drawing the bond dipoles, they will look like this. In trigonal planar, we know that all of the angles are equal. So the bond dipoles will cancel. And since they have all identical domains, this molecule is nonpolar. Next we have OF2, and this has 20 valence electrons. So this is the Lewis structure, and there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 valence electrons, and they all have octets. Fluorine is more electronegative, so it will get a partial negative charge. Partial negative, and the oxygen will get a partial positive charge. This means that the bond dipoles will point towards fluorine, so they will look like this. There are 1, 2, 3 domains on this, so it is also trigonal planar. But this one has a non-bonding pair, which means the molecular geometry will be bent. So we are going to draw the molecular geometry. So you have O, F, and F. These are your 2 bonding, and then this is your non-bonding pair. The bond dipoles will still point towards fluorine. This creates a net dipole pointing down. Since the domains are not all the same, there are bonding and there's a non-bonding. This has to be polar. This is the Lewis structure for BeCl2. There are 16 valence electrons, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is the Lewis structure for BeCl2. There are 16 valence electrons, so 2, 4, 6, 8, 10, 12, 14, 16. And this has an octet. So Cl has a partial negative on it because it's the most electronegative. And so this has a partial positive. This means the bond dipoles will point like this because the positive side goes to the positive and the negative side goes to the negative. This molecule has two domains. This makes it linear. So since it's linear, it is a 180-degree molecule, which means it will look like this, BeCl. Similar to what the Lewis structure looks like. The bond dipoles will still look like this, and the bond dipoles will cancel. Since all the domains are the same, the bond dipoles will cancel, making this non-polar. This is the Lewis structure for CCl4. There are 32 valence electrons, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And they all have an octet. Chlorine is more electronegative, so it will get the partial negative. And carbon will get the partial positive. This means that the bond dipoles will point towards Cl. It has 4 domains, meaning it will be tetrahedral domain geometry. And it will also be tetrahedral molecular geometry because there are no non-bonding pairs. Here is what the molecular geometry looks like for CCl4. All the domains are the same. That means the bond dipoles will cancel, making this nonpolar. This is the Lewis structure for O3. Since they are all the same, there is not one more electronegative to the other, so there will be no dipoles. We're going to check the Lewis structure. There's 18 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And they all have an octet. The domain geometry for this is trigonal planar because it has 3 domains. One of these domains is non-bonding, making it bent. So what this will actually look like is this, with a non-bonding pair on top. The domains are not all the same. These are bonding and this is non-bonding. This will make it a polar molecule. Finally, we can determine which ones were polar. We found that OF2 and O3 were polar. Some common mistakes that could occur is if you count the valence electrons wrong. If you do this, your Lewis structure will most likely be incorrect, and that will lead you to the wrong conclusion. Also, another mistake is if you count the domains wrong. So after you finish, if you're counting the domains and you forget that one is a non-bonding pair, you can get the molecular geometry wrong. Therefore, you would not know if the molecule is polar or non-polar.